Alright, today we will take up this topic of non-inertial forces, also known as pseudo forces, sometimes called fictitious forces, a concept in Newtonian dynamics that has actually quite a simple explanation, but is occasionally very confusing, especially because of lack of clarity as to where these forces come from and what exactly they mean. It will turn out that what we mean by a non-inertial force should really be called a non-inertial acceleration, and then once you multiply it by a suitable mass of a body which you are tracking, it becomes a force, apparent force acting on the body. And this, the whole origin of it is extremely simple. It has to do with the fact that Newton's laws of motion are valid in inertial frames. Newton's second law of motion, which relates mass times the acceleration for constant mass to the force acting on the body, is valid in an inertial frame, and an inertial frame is one in which the first law of motion is valid. So the question arises as to what happens if you have an accelerated frame, a frame that is that's undergoing an acceleration with respect to the family of inertial frames. What happens to Newton's law? What does it look like in that instance? And this is what we are going to address today. So to make matters simple, let us take a very simple specific example. I have in mind a coordinate system in an inertial frame like this, an x, y and a z, and I have in mind transforming from this frame of reference to a frame of reference that is rotating about the z axis at a uniform angular speed omega. So we have a new frame that is rotating with respect to this frame. The x and y axes become some other variables, x prime and y prime, or capital X, capital Y, while the z axis remains unchanged. So if you look at it from above, it looks like this. The original frame, and I am going to use small letters for the original frame. So here is x and here is y, that is the origin, and in the new frame of reference the x and y coordinates rotate at a uniform angular speed. So at some instant of time the coordinates, the new coordinates look like this. Let us call that capital X and this capital Y, and the rotation is a steady rotation. So at time t this angle is omega t. And then the question is, if I give you a mass m and it is undergoing some dynamics in the xy plane, what does it look like if looked at from the coordinate system with the capital X and capital Y, which are changing with time. So the way to transform from little x to capital X and capital Y is the familiar one. So I have x of t, and I am not going to write the t dependence here, it is explicit, it is implicit. This is equal to cos omega t times little x plus sin omega t times little y, whereas capital Y is equal to minus sin omega t times little x plus cos omega t times little y. Now we have dynamics going on in the little x little y plane. So we have a particle of mass m which then undergoes an acceleration a, which is a function of t, and that is equal to the force acting on it, and I will denote that by a small f here. That too in general is changing with time. Now of course I can resolve this into x and y components, and it is clear that this will imply that m times ax equal to f sub x, m times ay equal to f sub y in Cartesian coordinates. What happens here in this case? Well, the first thing we have to do is to differentiate these with respect to time, and this will immediately imply that x dot of t, and let us save space by putting overhead dots for time derivatives, x dot of t is equal to, there is one term in which the x and y get differentiated to give me little x dot and little y dot. So this is equal to, and let us put brackets to combine terms together suitably. So this is cos omega t times little x dot plus sin omega t times little y dot, and then there are two other terms which are plus. So we have an omega coming out, so plus, let us put the omega inside. So this is minus omega sin omega t times little x plus omega cos omega t times little y, and that is it. Once I differentiate it the first time, not only do these get differentiated because the particle is moving, has some velocity components, but in addition these two quantities, which are the coefficients relating the old coordinates to the new coordinates, also get differentiated with time, and this is what happens. Those terms are sitting here. Similarly, this will imply that y dot of t is equal to, again the same thing, minus sine omega t times little x plus cos omega t times little y plus extra terms y dot on this side plus extra terms which correspond to minus omega cos omega t times little x minus omega sine omega t. So, let us put a plus sign, and I want to keep all the minus signs right. So, let me put them in brackets, omega sine omega t little y in this fashion. So, we have two extra terms which come from the differentiation of the manner in which the coordinates, the new moving coordinates depend on the old coordinates here. Now, these of course x dot and y dot are components. So, Vx equal to x dot, Vy equal to y dot, and we will deal with these in a minute. What happens if I differentiate once again? I need to differentiate once again because I want to relate the acceleration in the new frame to the force in the new frame and find out if Newton's law is valid, or if it is not valid, as I suspect it will not be because of these extra terms, what are the extra terms that get in. So, this is the target, to find out to what extent can I write Newton's laws after I identify the new force in the new frame of reference and the new acceleration. So, the second derivatives x double dot of t is equal to, again I differentiate this term and this term first, and I get cos omega t x double dot plus sine omega t times y double dot. That is the first part, and then there are several other terms coming from the fact that I have to differentiate this, and of course I get twice this bracket now, because if I differentiate this I get minus omega sine omega t plus omega cos omega t, and this time I am going to get, if I differentiate these two, the dots on top, so there is a term which is equal to twice, and then whatever is inside the bracket, omega sine omega t x dot this time plus omega cos omega t y dot this time, twice, because once from this term and once by differentiating these two x's and the x and y there, and finally there is a third kind of term which comes from differentiating this quantity, that is minus omega squared cos omega t minus omega squared sine omega t. So, let us put a plus and a minus this guy here. Sorry, I should be careful. Times little x of course plus, so let us put the minus sign out, minus omega squared cos omega t sine omega t y, this fashion. So, that comes from differentiating x a second time, and let us differentiate y quickly a second time, and then you will see the structure of this whole thing. This is equal to, again I differentiate this part and this part, so it is exactly as before, minus sine omega t x double dot plus cos omega t y double dot plus twice, and now I am going to get these derivatives. So, it is going to be minus omega cos omega t x dot this time plus minus omega sine omega t y dot this time, and finally whatever I get by differentiating this and this a second time, So plus omega squared sine omega t, the minus sign goes away here, x, and then the derivative of this, which is minus omega squared cos omega t y, and that is it. We finished differentiating and we have got 6 terms on either side, because I started with 2 and I differentiate twice. Now it is immediately clear that if I multiply this by mass, I get here the component of the acceleration along the capital X direction in the moving frame. So this is equal to A, let us call it A, and this is the x component of the A sub x, that is mx double dot, the x component of, sorry, the let's be careful here. This quantity here is the mass times the acceleration as it stands, so let me call this m times A subscript x. By definition, A subscript x is x double dot, just as little a subscript x is little x double dot. So I am going to use, I have used capital letters for the rotating frame, small letters for the original frame, the inertial frame of reference. And similarly I multiply by m here, this is m times A y out here, and now I need to multiply this whole thing by m, so there is an m here, there is an m here, plus twice m here, plus twice m here, plus m times this, plus m times this, that is it. Okay. Now what is mx double dot? It is equal to, and I am going to do it right on this board itself to save myself space and time in writing, this is equal to A subscript little x, m times x double dot, and m times y double dot is A subscript little y times an m. So let us put m A little x plus sine omega t m A little y plus. But what is m A x? I know that in the inertial frame of reference m times A x equal to f sub x, m times A y equal to f sub y. This is Newton's second law, where f sub x and f sub y are the Cartesian components in the inertial frame of reference of whatever force is acting on this body of mass m. So I replace those here and I get f subscript x and f subscript y out here in exactly the same way. On this, in this equation I get this is equal to, once I multiply by m, I get f subscript x, f subscript y plus this term whatever is here. But what is this quantity here? This is the transformation of the force, the new x component, when you rotate the frame of reference through an angle omega t. Remember that the force is a vector. So it is immediately clear that f subscript x must be equal to cos omega t f x plus sine omega t f y, by the very meaning of the statement that the force is a vector. So this combination here by its very definition is the force, the new x component of the force, and let us use a capital F for that. So this whole thing goes away and I get F subscript x, and in exactly plus all these terms, and in exactly the same way I get here F subscript y plus a whole lot of other terms. So it is immediately clear that Newton's second law is not valid in the original form in the rotated frame of reference or the accelerated frame of reference. Remember, when you have rotational motion there is always an acceleration, you can't kill the acceleration. So this immediately implies that Newton's second law is not valid. So writing Newton's second law in this form tells you that MAX is equal to F subscript x plus some other piece, and similarly MA sub y is equal to F sub y plus some other piece, and these have the dimensions of force components, which is why these are called pseudo forces or non-inertial forces. They arise entirely from the fact that these coefficients in the expansion are time dependent and we have to differentiate them. So although there is no physical agency that produces these forces, for instance if F sub x is some kind of force which arises due to some electrical charges or electrical force, there is no such agency which produces these terms. These arise purely from the kinematics of accelerated motion. So since we multiplied this by m to produce forces, what really arose initially was differentiating these coordinates. We discovered there were extra terms in the acceleration. So I should really call these non-inertial effects of acceleration, pseudo acceleration if you like. But then once I multiplied by m, they become forces of some kind. They are forces in the sense that in the new coordinate system, the system does see these forces because its acceleration has this transformed force, the physical force, and then there are these extra terms here which are sitting here. But what do these terms look like? Well, you immediately see that this term, if I pull out an omega, and let us do that, 2m omega, and so this omega goes away, that omega goes away in this term alone. Remember that this is v sub x and this is v sub y. And what does it look like? It is clear that it looks like the velocity is also a vector. This looks like the y component, the transformed y component of the velocity. So the immediate identification, remember again our original rules of transformation for the x and y's, this tells you immediately what is going to happen. This thing here is v, capital V sub y here. So this is capital V sub y. So that part is identified, and this term here with a minus sign and an omega is capital V sub x. So there is some structure emerging here which tells you that in the new coordinate system, if you measure velocities, the velocity of the object multiplied by omega times m or whatever, then there is these extra terms sitting here, and that dimensionally these things have dimensions of force, and they are these two terms. And what are these terms like? Well, again you can see that this is minus m omega squared. So I pull out a minus omega squared, I get cos omega t x plus sin omega t y, that is capital X. So this is minus m omega squared capital X, and that is gone. And in exactly the same way, if I pull out a minus sign, this gives me minus sin omega t plus cos omega t. So this is minus m omega squared capital Y. So these are our final expressions for the x and y components of the acceleration. So mass times acceleration is the actual physical force transformed and looked at in the new coordinates, plus these extra terms or the extra forces if you like, non-inertial forces, or rather forces arising in a non-inertial system due to the kinematics, due to the fact that you are in an accelerated frame of reference. This term, these two terms, this or this, are the components of the so-called Coriolis force, while these two terms are the components of the so-called centrifugal force. Can we write this in a more elegant form than this? And the answer is yes. What is needed is the following. we have rotated about the z axis, so let us define an angular velocity to be equal to omega times E sub z. That is equal to the angular velocity and what is this term here then? The omega is a component of the angular velocity, the z component. So if you consider what omega cross v is, this is equal to omega E subscript z, small z or capital Z does not matter, it does not change at all, cross, and here you have Vx Ex plus Vy Ey here, and this quantity is equal to Ez cross Ex is plus Ey, so it is omega, this is a cross product Ey, and then Ez cross y is minus y cross z, which is x, so minus omega Vy Ex in this fashion. This is the vector, of course. We have here 2m omega Vy sitting there, so it is minus the x component of omega cross v. So I could remove this and write it as minus 2m omega cross v, the x component of it, because we had a Vy and that was minus omega Vy, and this is equal to, this term here is minus Vx Ey, and it's sitting, Vx is sitting there, so it's minus 2m omega cross v, the y component of it. So you see we are beginning to get a structure here. M times A, the x component, is F, the x component, there is a 2m omega cross v, the x component, and ditto here on this side here. It remains to identify this, and it is clear here that these x and y are the components of capital R, the new coordinate. If I call capital R has x and y components given by this quantity and this respectively. Well, it is a little more intricate than that. Let us put the structure down. If you look at what omega cross R is and use the vector triple product identity, then it is equal to omega dot R times omega minus omega dot omega, which is omega squared times R, and that is precisely what we have here apart from the factor m. Omega dot R is 0 if R has only x and y components, as we have assumed. We have said this object is moving in the xy plane, and that does not change, it never gets into the z axis. So these two are components of omega cross R, the x and y components respectively, with a minus sign. So let us write this as minus m omega cross R, the x component, and minus, sorry, plus, because the minus sign is already there. It's this minus sign which is already sitting there. So plus m times omega cross R, the y component. So we have a result now which says that in vector form the dynamics will look like this. What originally looked like m a equal to F now looks like that goes over into m times a, the acceleration, equal to the force F out here minus 2m omega cross v, the velocity in the new frame. So everything in this equation refers to the new frame of reference, the rotated frame of reference, plus m times omega cross R. That term is the Coriolis force, and that term is the centrifugal force. And that's it. So we have these two extra forces, apparent forces if you like, pseudo forces, non-inertial forces, whatever you call it, appearing entirely because of the fact that you have moved over to an accelerated frame of reference in which Newton's law is not m times a equal to the force applied or the external force, but there are these kinematic contributions here. When I multiply those accelerations by m, I get forces, effective forces. These forces do exist and they do act on the body as seen in the rotating frame of reference. The one point to note immediately is that if in the rotated frame of reference the object does not move, in other words if v is 0, the Coriolis force is 0 identically, and you have the centrifugal force that is always present no matter what. Even if you have a static object, it does not move in the new frame of reference, it still experiences this force, this term is still present. So the way its coordinate is related to its acceleration, there is this extra contribution here. And of course in the simple instances we have looked at of a constant rotating, uniformly rotating xy plane, this thing reduces somewhat minus m omega squared, the corresponding component of r in that form. But this is the general form in general. For arbitrary omega, no matter what, this is the general formula here. We need not now restrict ourselves to the xy plane or make any rotation. There is one assumption we have made, namely we have rotated this frame at a constant rate, angular speed. So the question is, what happens if I also change the rate of rotation or change even the axis of rotation as a function of time? There is one more pseudo force or inertial force, it is called the Euler force, and it is dependent on omega dot, as you would expect. I am not going to write that down since that is beyond the scope of what I want to say here. These are the most common forces here, and we can actually compute these quantities. Basically what we need to compute is the correction to is the acceleration, the centrifugal acceleration. We can estimate what this centrifugal acceleration is in various cases. The most common example of course is what happens on the center of the earth, and let us estimate that immediately. So we have the earth rotating about its axis, polar, that is the equator, and let us look at what happens to a point on the equator, because then we have to worry about the total radius of this earth. On the other hand, if you are at this latitude, it is only this axial distance that effectively contributes to the rotation, that is the one that appears in this formula, the r. So what we need to compute is what is omega squared r in the case of a point on the equator of the earth. So omega squared r on the equator is equal to 2 pi divided by the time period, which is 24 hours, and 24 hours as you know has 86,400 seconds. So we need to square this and multiply it by the radius of the earth, and the radius of the earth is 6,400 kilometers, so it is 6,400 multiplied by 10 to the power 3 in meters. And it is not hard to see, this number is well known. This is approximately 3 times 10 to the minus 2 meters second to the minus 2. That is the correction, these units. So given that little g is of the order of 10 meters second, this is like 3 parts in 1,000, the correction. More precise number is between 980 and 983. At the pole this correction would not be there, but at this equator it is maximum. So it is a small correction to the force of gravity here, and it is caused by the fact that there is this outward fling of due to the rotation of the earth. You are not in an inertial frame, but you are practically in an inertial frame because this correction is pretty small compared to little g, which is of the order of 10 meters second. So the ratio is of the order of 10 to the minus 3, and therefore you are all right. What happens now when the earth goes around the sun? That too is now a rotating frame of reference. So we can compute what happens there quickly. So orbit around the sun, orbit of the earth around the sun, and we need to compute omega squared r. So omega in this case is 2 pi divided by a year, and a year is got 365 days multiplied by 8600 whatever. This is of 3.15 into 10 to the 7 seconds. That is a useful figure to remember always, because 3.15 is pretty close to pi, and you can cancel the pi's on top to get an order of magnitude estimate. So that is omega, and r, so let us put omega squared r. So this thing squared times r is the rate, is the distance from the sun to the earth, and this is 150 million kilometers. So it is 1.5 into 10 to the 8 into 10 to the 3, so that is into 10 to the 11, and this is what we have to compute, and this is of the order of 10 to the minus 3. Again, a very small correction. This acceleration is very, very small compared to little g. Well, that is not the end of the story, because the sun goes around the center of the galaxy. So one could ask, is that going to make a big difference? Well, that is going to be hopefully a much smaller contribution. So sun around galactic center omega in this case is 2 pi divided by the period around it takes to go. That is 250 million years approximately. So it is of the form 2.5 into 10 to the power 8 times 3.15 times 10 to the power 7, that is in seconds. This whole thing is squared multiplied by the distance from here to the center of the galaxy. Well, this galaxy is of the order of 100,000 light years in terms of its diameter, and we are about 2/3 of the way from the center, so perhaps about 30,000 light years or so. So this is 3 times 10 to the 4 light years, and a light year 10 to the 7, so this is of the order of 10 to the 16 meters, and we need to compute this, and this of course immediately shows it is extremely small. This is of the order of 10 to the minus 10, 10 to the minus 9, 10 to the minus 10, etc. meter second. Okay. So again, a very small correction, very, very small correction due to this non-inertial force, the centrifugal force. You could ask what happens if you had much more intense gravity and much faster spinning. So as a little exercise, calculate what happens when this is a pulsar, 10 kilometers in radius, so r equal to 10 kilometers, and it is a millisecond pulsar, so the thing takes 10 to the minus 3 seconds is the time period. And you need to now find out what is omega squared r in this case, and I leave you to figure out what happens on the surface of this and compare it with the gravity there, assuming that the density equal to nuclear density. So say 100 protons in a volume which is whose linear dimension is 10 to the minus 15 meters. So compute that and find out what the correction is. In other words, find out what omega squared r divided by little g is on the surface of a pulsar, a millisecond pulsar, that is a 10 kilometer solid object rotating of nuclear density rotating at the rate of a millisecond. That is an interesting exercise to look at.